Dear students, today we will discuss about solar radiation and sunshine measuring instruments. So, before we start our topic, let us summarize what we have discussed in the last class. In the last class, we are discussing about the propagation of solar radiation from the sun surface to the earth surface. So, how solar radiation is propagated? So, there what we have discussed, so we had this earth atmosphere and then earth is here and sun was here, okay. Sun emits this short wave radiation and this is the earth atmosphere, aerosols, H2O, carbon dioxide, carbon monoxide, oxygen, then we have ozone, all the elements will be here and then particulate matter. Then some of the radiations which is unaffected by this earth atmosphere and it is directly striking on the earth surface. And then some of the radiations when it travels, then it scatters in the earth atmosphere and then this radiation is redirected in all the directions and the intensity of this radiation decreases. Okay. And then from the earth surface this long wave radiation is propagated and it is captured in the earth atmosphere. So, if we draw this spectral emissive power versus lambda for extraterrestrial region. So, the region which is above the earth atmosphere is called extraterrestrial region. Extraterrestrial region. And just below the earth atmosphere we will have terrestrial region. Terrestrial region. Okay. So, here if we draw this curve, this will be something like this. So, this is maybe 10 to the power of 8, then we have watt meter square and then micron. Okay. And this plot is for short wavelength radiation and at 6000 Kelvin. So, this is the radiation spectrum when radiation is coming from the sun surface and this value is 5 and this is of course in micron and maybe we have 10 here and it goes up to 30. And in this case when we draw this spectrum curve for long wavelength radiation after radiating from the earth surface, then we will have something like this kind of profile. So, this peaks will be at 10 micron and this will be at 288 Kelvin and this may be at 30, okay. And of course, this is spectral emissive power, unit is watt meter square and micron. So, here solar radiation is propagated. What happens in the earth atmosphere? Some of the radiations is unaffected by this earth atmosphere and it is directly striking on the earth surface. So, the kind of radiation what is directly striking on the earth surface is known as normal radiation. And when this radiation is scattered because of this aerosol present in the earth atmosphere, intensity of the radiation reduces. So, this radiation intensity is known as diffuse radiation. So, when we add this diffuse radiation plus normal radiation, it becomes global radiation or we can represent in capital IG. Okay. So, two kind of radiations we are getting. at the Earth's surface. One is normal radiation and other one is diffuse radiation. If we combine both, then what we call is global radiation. So, we will study the kind of instrument used for measurement of diffuse and global radiation and normal radiation. Also, we have studied in the last class the relationship between sun and earth. So, how solar radiation is propagated from the sun to the earth, and we also studied the distance between, that means average distance between sun and earth. Okay. Also, we know the radius of the sun and radius of the earth. So, by utilizing this concept, what we can able to calculate is black body temperature of the sun by utilizing the concept of energy emitted by the sun and then amount of energy received by the earth surface. So, this has been demonstrated in the last class. Also, we have studied a very important parameter called air mass. So, air mass is very, very important, and we must know the significance of those air mass 0, air mass 1, air mass 2, air mass 1.5. So, what does this air mass 0 indicates? That means that is the spectrum, the solar energy radiation spectrum above the earth atmosphere. That means in extraterrestrial region where the radiation is not affected by the earth atmosphere. So, it is represented by AM0. So, first let me write the expression for air mass. So, this will be something like 1 by cos theta, what we have discussed in the last class. So, for example, if we consider this plot and if we represent this as A, this point, and this is B and this is C, that means AB by BC is 1 by cos theta, okay, and this is known as air mass, what is written here. So, if theta is 0 degree, means this angle is 0, this angle is 0, means what will happen? Then cos 0 is 1, so AM will be 1. That means this spectrum is known as AM1. Okay. And AM0 already we have defined. So, in this plot what we can see here, this red colored line is for AM0, which is this spectrum is available in the extraterrestrial region, and blue colored profile is for AM 1.5. Why AM 1.5 is very important? Because at this air mass normally all the solar devices are tested. Of course, we need to consider the radiation. So, at what radiations normally this is tested? This is normally tested at 1000 watt per meter square, but air mass 1.5 need to be maintained for standardizing these solar devices. Also, let us summarize the monthly variation of solar radiation flux in the extraterrestrial region. Already we have studied this expression and we understand how this extraterrestrial region or extraterrestrial intensity is varying with number of days. We can also plot this variation. So, for example, say for January, starting from January to December. So, here, so January, maybe I will say January here, then I will have February F, maybe March here, April, May, then you have June, then you have July, then you have August, you have September, then we have October, then we have November, then we have December. Okay. So, January line may be here. So, this vertical line is for extraterrestrial radiation. So, I will write IEXT, this is something like this here. So, if we use the January 1 at the end of the month, maybe n is equal to 31. So, there are some recommendations. So, sometimes what happens, we need to analyze daily how this radiation is varying. What is the extraterrestrial region, extraterrestrial radiation on day 1, maybe 1st January, what is the extraterrestrial radiation, 2nd January, what is the extraterrestrial radiation. So, that way you can calculate, but no, people have recommended that if we take a particular day of a particular month as a representative day, so on that day we can calculate what is the extraterrestrial radiation for the particular month. So, here maybe at the end of the month, maybe we can consider, we can see how this extraterrestrial radiation is varying. So, of course, this unit will be watt per meter square, because solar constant is also 1 watt per meter square. Its value is 1367. This is a modern value normally we use. So, these variations already you have understood why the variation is happening. So, maybe scale I can start from 1300 and we can go up to 1420. So, I will just write a qualitative curve here. So, this moves something like June will be June, July, okay, June will be lowest. So, June will be lowest, this will be something like this. So, here every point we can get that extraterrestrial value. So, this plot will be something like this. So, sometimes we are not bothered about the variations, only we take the ISC value, but when we are doing very precise calculation, of course, we need to know how this extraterrestrial radiation is varying with month. Okay. Now, let us discuss our today's topic is solar radiation and sunshine measuring instruments. So, here in order to understand the mechanism of absorption, scattering and attenuation coefficients, people have done extensive research, but still it is very difficult to predict the radiation on a particular day at a particular time. So, the designer has decided to do something else, so that they can design their equipment for a particular region. So, there are many options. One of the option is make measurement over a period of time. So, we can get long term data, maybe 10 years data, maybe 20 years data. If we extend the duration of the data, then of course, our accuracy level will increase. And second option is use the available data for some other locations having reasonably similar climatic condition. So, if we know some of the locations where climatic condition is similar to the climatic conditions where we are planning to design or install some kind of solar equipment. So, we can take those data and we can do the analysis. And third option is we can use empirical predictive equations. So, there are numerous correlations available to relate meteorological data and radiation data. Meteorological data means like what is the sunshine duration, what is the precipitations. So, if we get those data, we can relate with the radiation data and then we can calculate what is the, or we can estimate the kind of global radiations falling on a particular location at a particular time. So, these are the considerations normally designers adopt for designing an PV system or maybe solar thermal system. So, as far as atmosphere at the earth surface is concerned, primarily there are two atmospheres. So, an atmosphere without clouds, that is cloudless, so sky is very clear, and another category is an atmosphere with clouds, that may be partially or fully clouds, but this mechanism of scattering and absorption are same for both the cases. But of course, intensity of solar radiation will be higher in case of an atmosphere without clouds, that is in clear sky. Okay. So, these considerations will be studied, and based on these classifications there will be many more correlations. We will study one by one in the later slides once we finish this part of the course. So, now come to the solar radiation received on a clear sky. When sky is clear, the way you are expected to get this kind of profiles. So, in the sunrise radiation will be very, very low, and then it will slowly it will increase and it will reach a peak at the noon, and then it is decreases when it reaches to 0 when sunset occurs. Okay. So, this profile is a very standard profile, okay. And this kind of profile if we get, that is very good, that is very good for solar installations. Here what happens, this curve may be whole good for both diffuse and normal radiation. So, of course, if we consider this is for normally free radiation, so diffuse component will be something like here. Okay. So, there are many things to be studied in this curve. So, normally what happens, we are sometimes telling like what is the solar radiations. So, solar radiations may be solar irradiance or solar irradiation. So, solar irradiance is instantaneous. So, what is the value of say normal radiations at this moment? Okay, maybe something like 700 watt per meter square. Okay, that is instantaneous values. But this instantaneous word is valid for 1 hour. So, since this solar radiation is not very much in 1 hour duration, so this solar irradiance is whole good for 1 hour variation. Okay. And of course, we are interested for daily variations. What is the daily sunshine variation, or what is the daily global radiation variation, what is the daily diffuse radiation variation. These informations are of course required when we are doing that kind of calculations. Okay. So, now my concern is, so one is solar irradiance and second one is solar irradiation. So, instantaneous value is solar irradiance, and when we integrate over the time, that becomes solar irradiation. Okay. So, this plot is for clear day when no cloud is covered, so sky is clear. In this case, this is partially cloudy sky. What you can see, there are lots of peaks and valleys. So, there is no uniform patterns. So, under this condition, it is very difficult to design a solar collectors, that may be PV collectors, but may be solar thermal collectors. So, this kind of erratic behaviors are observed. So, red color indicates global radiation is sum of diffuse and normal radiation, and this yellow colored is direct radiation, and this blue color is for diffuse radiation. You can see the variations of this irradiance, okay, of the day. Now, since we have already accustomed about different kind of radiations, direct radiation, then diffuse radiation, and then reflected radiation. So, let us learn something details on those radiations, and we will learn how those radiations are measured by using different instruments. So, if we have to measure direct radiations, then we have to use pyroheliometer. For diffuse radiation, we have to go for pyranometer, and of course, reflected radiations can be measured by using different instruments. So, these are the different instruments used. This plot is for pyroheliometer, which is very, very costly, and it will give normal radiations falling on the earth surface, and this is pyranometer. Pyranometer is mostly used in many of the experiments and other applications, and of course, same instrument pyranometer can be used for diffuse radiation measurement by using a shading ring. So, we will discuss this in the next couple of slides, and of course, we need a sunshine recorder to know the duration of the sunshine, which is important, how long our sun will retain. So, this is a special kind of instrument called sunshine recorder used for measurement of duration of the bright sunshine. So, now come to the pyranometer, so which is used for measurement of both global and diffuse radiation. So, here as you can see, this is the instrument used for measurement of both global and diffuse radiation. So, here what happens, one black absorber is used here, as you can see here, that is a black absorber, it is a black absorber, and these are the glass, semi hemisphere glass. Okay. Normally, if we draw a line here, so this diameter is about 50 mm outer diameter, and this is about 30 mm, and this is a circular disc kind of absorber. So, it is about 25 mm diameter. So, when solar radiation is exposed here in this black absorber, its temperature rise will be there. Okay. So, this rate of rise will continue till the heat loss by conduction, convection and radiations are equal. So, this mass transfer has to be there. So, in order to measure this, thermopiles are used. So, at the beneath of this absorber, one thermopiles are attached. These are thermopiles. Okay. Then if we write very clearly, so this is a black over, and then there is one, and here we have absorber, and this is a thermopile or a sensor, and this is a guard plate. One guard plate will be here. Guard plate. So, here I hope that you know the thermocouple principle of thermocouples. So, when we have two dissimilar metals, so this is one maybe one material, and we will have, I will use some another color, maybe this one. So, we will have two different materials, and we maintain at two different temperatures, maybe I will remove this and maybe I will use this, and if we connect one millivolt, and this is at temperature, this may be T1 and this may be T2. If maybe T1, these two are different, T1 and T2 are at different temperatures. Okay. And if these two are at different temperatures, then EMF will be generated. Okay. So, this is the principle of thermocouple. Thermocouple. So, how does a thermocouple work? If we have two dissimilar metals and we keep the junction of both at two different temperatures, then EMF will be generated. So, here what happens, same principle is applied here. So, thermopiles are used. Thermopiles are nothing but, if we use many thermocouples in series, that becomes thermopile. So, these thermopiles are connected at the beneath of this absorber plate, and then when solar radiation is exposed, then this part, blackened surface will be heated up, and then heat will transfer to this sensor, that is thermopiles, and one bead is maintained here, or one junction is maintained here, and that is some kind of spherical or circular junction, and other junction is maintained just below this guard plate, and this bead is maintained in such a way that this is not exposed to the solar radiation. Okay. So, a value of 0 to 10 millivolt is generated, and this is accumulated with time, and then finally, that can be converted to watt per meter square by using some kind of fitting coefficient. So, principle is very simple. So, we use the concept of thermocouple, that means thermopiles are used to measure the rise in EMF. So, this is calibrated, and finally, we can calculate in terms of watt per meter square. So, the kind of radiations we will get is called global radiation. If we set this part, we will not allow this semicircular strip we use to set this glass envelope, so that direct radiations cannot come and strike on this black surface. So, only radiation will come from the other side, this is a scattered part or diffuse radiation. The kind of radiations we will get under this condition is called diffuse radiation. Okay. So, we have to set this glass envelope, so that direct radiations cannot strike this glass envelope. And there is a procedure how to install this shading ring. So, this is called shading ring. So, this shading ring is used for measurement of diffuse radiations. There are many applications of this radiation, like material testing research, assessment of efficiency of solar collectors and photovoltaic devices. Now, let us learn something about pyroheliometer. So, this is a very good instrument and very costly instrument, and normally this is used for measurement of beam solar irradiance. So, this sunlight enters, as you can see here, sunlight enters through this tube. So, I can write, or I can make this kind of arrangement how this can be measured. So, we will have absorber, and then we will have one more, this is absorber, and then we will have thermopile. Okay. This part is thermopile, and we will have some kind of support here, and then radiation will come and then strike, and then this radiation will come and it will be here, and this is absorber, and of course, we need some kind of arrangement. So, to see whether it is aligned or not. So, we can see from here, and we need some kind of tracking device here, this kind of tracking device. So, and this angle is called acceptance angle. So, what happens if you see this figure? So, this structure is something like that. Solar radiation pass through this, and this is the tube through which solar radiation penetrates, and there is a absorber. Okay. So, special kind of materials are applied here in order to increase the absorptivity, and this thermopile is attached here. Okay. So, this one, as discussed in case of a pyrometer. So, one junction is maintained here and other junction is somewhere here, which should not be exposed with solar radiation. So, we can get the millivolt generator or EMF generation here. So, once we know the EMF, then we can calibrate, and then finally we can get in terms of watt per meter square. So, in order to hear what is the difference between pyrometer and pyroheliometer. So, here we need to track the normal solar radiations. Only normal solar radiation is allowed to enter in this tube, and we can measure the intensity of the normal solar radiation. Of course, some amount of diffuse radiation also penetrate, but that is a very negligible amount. So, the kind of radiation what you will get by doing these calculations or measurement will get normal radiation. So, this is 2 axis tracking. So, two axis tracking. So, what happens, we can access into 2 dimensionals, one is this way and other is this way. So, two ways we can track it in order to capture the normal radiation. So, this, as I have written here, sunlight enters the instrument through a window and is directed on the thermopile, which converts the heat to the electric signal that can be recorded. The signal voltage is converted via a formula to measure watt per square meter. And of course, we need to use solar tracking devices to track the normal radiations. And already we have explained what are the components. We need sensors like thermopiles and protecting cap. Okay. And as far as applications are concerned, this kind of instruments can be used in meteorology, material testing research, assessment of the efficiency of the solar collectors and photovoltaic devices. Now, let us learn the other instrument which is used for measurement of duration of sunshine hours in a particular day. So, here we used the Campbell Stokes recorder. So, in this measurement we will have one spherical bowl shape structure and we will have some kind of strips. So, solar radiation is focused by using this glass sphere to a point on the paper strip which is held concentrically with respect to this glass envelope, and there is a groove where we can fix this paper strip. Whenever there is a bright sunshine, so that image form is intense enough to burn the strip. So, as the sun is moving in the sky, then this burnt rays will also move from the original focal point or burning point till burning takes place. So, this burnt rays, this length of the burn or burnt rays is directly proportional to the duration of the bright sunshine hours. So, that way we can measure the duration of the bright sunshine hours. Okay. So, this device that records the amount of sunshine durations at a given locations and a burnt rays whose length is proportional to the duration of the sunshine is obtained on the strip. So, once we know this burnt rays, then from that you can calculate the duration of the bright sunshine hours. So, this is very good instrument. So, basically what it does, though this sphere is used to form a image here, okay, and this strip is time specific. So, same strip cannot be used for throughout the years. So, there are many strips, so which can be applied for particular duration, maybe so January to February one strip, then February to say April one strip. So, that way there are different kind of strips can be used for measurement of brightness of the sun for a particular month. So, this slide shows the different kind of sensors used for radiation measurement. So, we can have heat flux sensors or thermopile detectors. So, structure of those sensors can be seen. So, this is something like that, and heat flux sensors are something like that. And there are sunshine duration sensors which is available in the market. This kind of sensors are also used for measurement of brightness of the sun or sunshine duration. So, now let us discuss something about solar radiation data, because we must know the unit used for measurement of solar radiation, and then what is the source of solar radiation data. So, normally we use watt per meter square as a standard unit for solar radiation flux, but one very interesting or very renowned scientist Shimul Langley, who made the first measurement of the spectral distribution of the sun. To honor his contributions, there is a unit called Langley's, which is also used to represent solar radiation flux, which is also used to represent solar radiation flux. That is, 1 Langley is equal to 1 calorie per centimeter square, and if we convert to kilowatt hour per meter square, it is something like 1.163 into 10 to the power of minus 2 kilowatt hour per meter square. So, that means 1 Langley is equal to 1.163 into 10 to the power of minus 2 kilowatt hour per meter square. So, if we see in terms of Langley's, the amount of energy received in Indian context, so this is about 450 Langlays per day for summer season if we consider global radiation. So, that means that global radiation received in India is about 450 Langlays per day, and peaks is about 600 Langlays per day, and this is maybe in the month of May, June. And of course, the place like Rajasthan and Gujarat are mostly exposed to the sun, so they are receiving more Langlays per day compared to rest of the countries. And in winter months, this average global radiation is found to be about 300 to 400 Langlays per day. But when we talk about diffuse radiation, so annual average diffuse radiation received in India is about 175 Langlays per day, and maximum is about 300 Langlays per day, and this is maybe in the month of July, and Gujarat is the place where we get maximum solar radiation. And we get minimum values of 75 to 100 in the month of November and December. That means 75 to 100 Langlays per days. And of course, there are many sources from where we can get the radiation data. There are institutions where they generate radiations data, and they compile it, and if we buy it, then of course we can get all the spectrum of the radiations. So, as far as Indian map is concerned, we can see here, so which portion is having higher intense radiations. As you can see, this portion is very deep or say very highly intense radiation fall in this region, and of course this locations, this part like southern part, and other part as you can see 5.5 to 6 kilowatt hour per meter square per day is received in those locations, and about 5 to 5.5 is about these locations is about this is about 5 to 5.5 kilowatt hour per meter square per day. So, here it is somewhat higher, it is about 6.5, is very good for solar kilowatt hour per meter square per day. And you can see these portions are very erratic because of climate is somewhat different. So, here about 3.5 to 4 kilowatt hour per meter square per day is received. So, that way it is very difficult that same instrument cannot be, or same product we can install in all the places, but we cannot expect that the same efficiency we will get through the locations. So, it is radiation specific. So, yeah, so radiation data we can get from many sources, and we can do our calculations, and we can design our solar components based on the radiation data. And one very interesting things we need to discuss about the instantaneous and global diffuse flux. So, normally we use I, Z and I, D. So, this is the instantaneous global flux, and this is the instantaneous diffuse flux, okay, and unit is watt per meter square. Okay. So, as already we have discussed, this instantaneous nomenclature can also be used for hourly variations. Okay. So, it is assumed that in 1 hour time this radiation is not varying much. So, that is why we can use the same terminology for representing hourly values of global and diffuse flux. So, these expressions are whole good for both instantaneous global and diffuse flux as well as hourly values of global and diffuse flux and ID. Sometimes we are interested to know the daily global and diffuse flux incident over a whole day. So, under that conditions we use this kind of terminology HZ and HD. So, this is all about daily global and diffuse flux incident over a whole day. Okay. So, if we see precisely these units, so these two units are something like kilowatt hour per meter square per day, or kilojoule per meter square per day. Okay. And here what we can write, unit of these hourly values of global and diffuse radiations are something like kilowatt hour per meter square hour, or maybe kilojoule meter square per hour. On the top of it, sometimes maybe researchers are interested about average values of hourly values of global and diffuse radiations. Under that conditions, what we will use? We will use Ig bar and Id bar. So, this is for average values of hourly global and diffuse radiation flux. Okay. Also, sometimes researchers are required average values of daily global and diffuse radiation. If we are concerned about average of daily global and diffuse radiation, then what we will use? Hg bar and Hd bar. These two are very, very important, because most of the cases we need to use the average values, because in a single day data we cannot design a solar system. So, we need a long range data, and we need average values of those data. So, once we have those average values, then we can use it for calculations for amount of radiation what is received on a particular locations, and which is finally useful for design of collectors. So, what influences the solar radiations? That is, first thing is Earth's sun distance. This has been demonstrated how this is influenced this solar radiation, because we can see the variation of extraterrestrial radiation with respect to the days. So, it varies with time and relative tilt and time of the day. So, these are the parameters which influences the solar radiations. And of course, we define irradiance and irradiation. So, irradiance is the rate at which radiant energy is incident on a surface per unit area of the surface, and irradiation is when we integrate this irradiance over time, what we get, that is irradiation. And sometimes we use insolation also. The terminology insolation is used, which applies specifically to solar energy irradiation. So, these terminologies are used in most of the cases when we deal with radiation studies. Now, come to the summary of this lecture. So, today what we have learned about different instruments used for measurement of solar radiation. So, pyrheliometer is used for normal radiation or direct radiation, and pyranometer is used for diffuse and global radiation. By using shading ring, we can measure diffuse radiation, and without using shading ring, we can measure global radiation. And of course, we have learned how duration of sunshine is recorded by using a sunshine recorder. So, sunshine recorder is very important instrument for understanding or measuring the brightness of the sun or sunshine duration. And also we have studied the concerns of solar equipment designer. So, what condition solar equipment designer has to adopt for the analysis, because there are options. So, we have to use the appropriate options for designing the system and designing the components. And also we have studied the units and units of radiation. So, this is watt per meter square. So, sometimes we have to represent average of hourly, sometimes we have to represent average of daily, and sometimes instantaneous values we need to measure, and of course radiation data, how these radiation data are applied and from where this radiation data can be obtained for the further analysis. So, thank you for watching this video.